Do you remember that scene from Interstellar, where one day on a planet near the black hole was equivalent to 7 whole years back on Earth? It wasn't some Hollywood sci fi magic, it was actually physics. And the same thing is happening right under your feet as we speak. In our last video, we learned the relationship between speed and time. Einstein basically told us the faster we move through space, the slower we will move through time. But that was not all. Einstein realized something very important. There was another factor that could warp time. It's none other than, you may have guessed it, gravity. Now, what if I told you that the heavier the planet is, the slower time ticks on its surface? You aren't just sitting on Earth right now, you're inside a giant warp in time itself. To understand how this really works, we need to first realize that Newton actually lied to us. Not exactly, but Newton told us that gravity is a force, an invisible force. That means we cannot see it, we can just feel it. It's like an invisible rope that always pulls us down back to the ground. Wait. Did I just say that Newton lied to us? But how is that possible? We have been learning his formulas and his laws in school, and so far it's the standard. To answer that question, well, actually, I'll answer this question at the end of the video. It's a very important question, but I'll answer it at the end of the video. Anyways, we will be first tackling the most important question of this topic. If gravity isn't a force, then what is it really? In simple words, Einstein told us that space and time are interconnected and they're like a fabric. And gravity is nothing but the curvature of the space time fabric. And this curvature in the fabric happens due to mass. The same thing Newton thought causes the force of gravity to act. All this information at once is probably really overwhelming, and I get that. Therefore, to understand this better, let's use a really famous thought experiment. Imagine that the space time fabric is a giant trampoline, and now we will place a bowling ball representing a massive star like our sun in the center. We would notice that there is a dip on the trampoline. Let's first take a smaller ball like object, let's say a marble, and place it at the edge of the trampoline. What do we notice? We notice that this small marble will roll straight down from that edge to the center where the bowling ball is because of the dip in the trampoline. You know what? Let's repeat that. But this time, instead of just placing the marble at the edge of the trampoline, let's instead give it some initial momentum. This time, we will instead roll it across the fabric of the trampoline. This time, what do we observe? We observe that instead of just falling directly to the center to where the bowling ball is, it will rather revolve around the bowling ball a couple of times before arriving at the center. This is exactly what happens on a larger scale as well. The space time is being curved itself due to the masses of these objects. The bend itself is what gravity really is. So, Earth is not really pulling you down with some force, it's bending or curving or warping the fabric of space time itself, which leads you falling right back down to the ground. That still may have been a bit tricky to understand. So, instead, to differentiate between Newtonian gravity and Einstein's theory of gravity, let's look at another thought experiment which I created myself. Now imagine this. You and your friend go out on a stroll. You both are walking on the neighborhood path which is in a straight line. Across the street, there is an ice cream truck. Your friend really wants to get some ice cream and they want you to get some too. But you, on a diet, are not interested. Therefore, what your friend does is they grab you by the hand and forcibly take you across the street to get some ice cream. Now, what I just said is what you can think of as Newtonian gravity. Now, so Einstein's theory of gravity, or you would say general relativity, says that it is not a force. So, what's happening in Einstein's case? Let's take the same situation. You and your friend go on a stroll. You both are walking down the street in a straight line, and your friend sees an ice cream truck. Now, since since gravity is not a force, your friend does not simply drag you across the street. He rather takes that straight path that you are walking on and bends the path itself and points it towards the ice cream truck so that you continue walking straight and instead of, going where you wanted to go, you would get curved by the path itself. Your path itself would be changed and you would slowly walk to the ice cream truck against your will. Obviously, what I just explained is not physically possible. A person cannot just simply change the path you're walking on. But this is literally what gravity does. What Newton told us is that gravity is a force, which I explained is your friend forcibly taking you and pulling you across to the ice cream truck. And what Einstein tells us is that it's not a force, it's literally the changing of path that a planet or any other celestial object follows. What happens is that the path itself is being changed. Like I said, your friend, he literally changes the path. He takes that straight path you're walking on and bends it or warps it in a way that it leads to the ice cream truck. So, in your perspective, or from your perspective, you would be still walking in a straight line, but you would ultimately still reach the ice cream truck because of so called gravity, which your friend is. So, to finally put this in conclusion, Newton's gravity or Newtonian gravity tells us that gravity is a force, whereas Einstein's general relativity tells us that gravity is not a force, but rather it is the curvature or warping of space-time itself due to mass. Now, let's get back to Einstein's relativity. Remember that space and time are interconnected. Therefore, if space warps, that means time is warping along with it. This would mean that the heavier the object is, the more space-time would stretch, and the slower time would tick. Since your feet are closer to the center of Earth, the gravity at your feet is stronger than the gravity at your brain or head. Therefore, time would move slower for your feet than it would for your head. Therefore, mathematically speaking, your feet are genuinely younger than your head, even though the difference is very tiny. It's nanoseconds over a lifetime. If you think all of this is theoretical, think again. We use this in everyday life. The GPS on your phone relies on the GPS satellites, which are just kilometers above the Earth's surface. This would mean that gravity is weaker there than it is on the surface of Earth. This would mean that time moves faster up there on the satellite than it does down here on Earth. Therefore, to accommodate for this, scientists have to set every clock on the satellite 45 nanoseconds ahead every day. If Einstein's general relativity didn't give us these equations, the scientists wouldn't have been able to figure out how time works differently on higher orbits of satellites. Therefore, they wouldn't have been able to artificially slow down their clocks. Thus, these satellites wouldn't be able to pinpoint the locations of our phone accurately. This would mean that our GPS or the directions given to us on the map app would be wrong by several kilometers. So remember, the next time you get lost using Google Maps, you can blame the curvature of spacetime. Now that we've tackled the main question and understood how gravity works and also understood Einstein's general relativity, let's move on to the next question. Why did Newton lie to us? Well, did he actually lie to us? To put it simply, Newton wasn't wrong. His equations are great approximations for everyday life, and we still use them today. Einstein's equations of general relativity are highly complex, but once you simplify them down by using smaller or weaker gravitational values, you would notice that they give you Newton's exact equations. This would mean that Newton wasn't wrong at all. In fact, Newton was right, and Einstein is also right, but you would use general relativity on a larger scale where Newton's gravitational theory breaks down. So now that we have understood what general relativity is, how Newtonian gravity is still correct and still very important, I would like to conclude this video by saying thank you, of course, and that I will be uploading more videos in the future. And if you like the video, please like and subscribe and comment down if you have any feedback and if you have anything to say at all. Thank you.